Okay, so you're trying to build an application, right? And not just any application, but one that needs to keep track of information, like user data or shopping carts.
Yeah, the stateful ones, those are the ones that get really tricky when you want them to handle
Hmm.
like a huge amount of traffic. We're talking scaling up to handle massive growth without the whole thing just falling apart.
And we've got a ton of research here today to help us break down exactly how to do that. So think of this as your cheat sheet to the really important stuff. We'll be looking at the architecture you need, some tips for scaling, ways to make sure it stays fast, and of course, how to test it all.
What really stands out to me is that it's not just about getting bigger servers or anything like that. You have to approach it in a smart way, kind of like building a house with a solid foundation first.
Right, yeah. The design at the very beginning is going to make a huge difference in how well you can scale horizontally. And a lot of what we're reading is talking about this idea of splitting up your data using techniques like consistent hashing.
Oh yeah, I've seen that one. It's like you imagine all your servers are in a circle and you use this hashing function to decide where each piece of data goes. And that way, when you add or remove servers, it's much less disruptive.
Exactly. But then you've got all these different pieces of data, so you've got to keep them all in sync.
You got it. State synchronization is key. So you'll see systems using things like the RAF protocol or Paxos, which basically let all the different parts of your system agree on the same information, even if a few of them crash.
That sounds pretty complex. How do you actually manage all that in a real system?
Well, there are tools for that. Like you'll see things like etc. or Zookeeper acting as a central coordinator. And if you're using Kubernetes, there's a whole thing called CRDs, or custom resource definitions, and a pattern called the stateful operator pattern that give you more control over how these applications scale.
Okay, so we've laid the foundation, but how do we actually make the scaling happen? Like, do you just sit there and watch your servers and then click a button to add more when things get busy?
Not anymore, no. These days, it's all about automation. You want the system to adapt to the load in real time. So instead of manually doing everything, you define custom metrics, like how long it takes to process requests or how many messages are piling up in a queue. And based on those signals, the system can automatically add or remove resources.
So it's kind of like a self-driving system, except for your application.
That's a good way to put it, yeah. Some systems even go a step further and use historical data to predict future load and scale up in advance.
Whoa. Like, they know that on Friday afternoon, everyone's going to be ordering pizza, so they get ready for it.
Exactly. One smart approach we're seeing is a two-tier system. You've got a core set of servers that are really stable and handle the critical state information. Then you have more dynamic nodes around that core, and those are the ones that scale up and down as needed.
That makes sense. Now, let's say you do need to add some new servers. You don't want them to just sit there empty, right?
Definitely not. You want them to be ready to go as quickly as possible. That's where all these state transfer optimizations come in.
So what, you just copy everything over from the old servers to the new ones?
It can be that simple, yeah. But there are also more sophisticated techniques like pre-warming, where you start preparing a new server in the background even before it's officially added to the cluster.
Oh, that's smart. So it's kind of like warming up your car on a cold day before you drive it.
Exactly. And you've also got things like incremental state transfer, where you only copy over the changes rather than the whole thing, and state checkpointing, which is like taking snapshots of the data so you can recover more quickly if something goes wrong.
Okay, that all makes sense for getting new servers up and running, but what about while it's all happening? We want to make sure everything stays fast, right? Like if we're scaling up because we're getting more users, we don't want those users to experience a slowdown.
Right. That's why maintaining performance during scaling is so important.
Hmm.
A simple approach is just to over-provision your resources, so you have a buffer to handle spikes in traffic. But there are also more adaptive approaches.
Like what?
Well, there's something called adaptive back pressure, which essentially lets your system push back on incoming requests if it's starting to get overloaded.
Oh, that's interesting.
Yeah, it's like a way of saying, hey, hold on a second, let me catch my breath. And another thing is prioritizing different types of workloads. So if you have some requests that are really critical, you can make sure those get handled first, even if the system is under heavy load.
Now, all of this is great, but how do we make sure that the information stays consistent? Like if we have different servers handling different parts of the data, we don't want them to get out of sync.
Absolutely. You got to have those data consistency controls in place. One common approach is to use strict quorum requirements. This means that a majority of the servers have to agree on any changes before they're considered final.
That makes sense.
And you've also got distributed locks, which help coordinate updates to really critical parts of the data. And then for some systems, you might be okay with a little bit of delay and consistency, so you'd use conflict resolution strategies to figure out what to do if different servers have different versions of the same data.
So it's all about choosing the right approach for your specific application.
Exactly. And there's also this thing called change data capture, or CDC, which is a way of tracking and propagating changes to the data in a really reliable way.
Now, we've talked a lot about the concepts, but what about actually implementing all of this? Like, what kind of platforms do we need?
Oh, that's a whole world in itself. But some things to consider are hyperconverged infrastructure, which combines compute, storage, and networking into a really tightly integrated package. You'll often see local NVMe drives in these systems, which are super fast for storage.
And what about Kubernetes? That's super popular these days.
It is. And for stateful applications, you'll often use something called stateful sets, which basically give each pod a stable identity and some persistent storage, which is really important for keeping track of that state information. And you can use things like anti-affinity rules to make sure your replicas are spread across different nodes, so you don't lose everything if one node fails.
So it's all about building in those layers of redundancy and resilience.
Exactly. And even little things like custom readiness probes, which check that your applications are actually ready to handle traffic after they start up, can make a big difference.
Okay, so we've got our architecture, our scaling mechanisms, our performance safeguards, our consistency controls, and our platform. What's next?
Testing. You got to make sure all of this actually works as expected. And I'm not talking about just running a few simple tests. You want to really push the system to its limits.
How do you do that?
There's this whole thing called chaos engineering, where you basically intentionally break things in your system to see how it responds.
It's like you just randomly shut down servers and see what happens.
Pretty much, yeah. It sounds crazy, but it's a really good way to find weaknesses in your system before they cause real problems in production. You also want to simulate real-world load patterns so you can see how your system handles the kind of traffic you expect to see in production. And canary deployments are a good way to test out changes to your scaling policies on a small subset of users before rolling them out to everyone.
It sounds like testing is super important.
It's absolutely essential. You don't want to wait until you're in the middle of a huge traffic spike to find out that your scaling strategy doesn't actually work.
So we've talked about designing for scale, automating the scaling process, optimizing how state gets transferred, keeping things fast, making sure data stays consistent, and the importance of testing. And it sounds like those are the really important parts of building a stateful application that can grow and adapt.
Exactly. It's interesting to think about how this all applies to other things beyond just software. Like, imagine a city that's growing rapidly. They have to figure out how to scale their infrastructure, their transportation systems, their public services, all while making sure things stay organized and efficient. It's a really complex problem.
And it's not that different from what we're talking about here.
Not at all. Or think about how a biological organism grows and develops. It has to manage all these complex processes, all while maintaining its integrity and functionality. So maybe there are some underlying principles here that we can apply to all sorts of systems, not just software. What do you think?
I think that's something for our listeners to ponder.
Yeah, definitely food for thought. Thanks for having me.
Thanks for joining us on this deep dive.